taking a glance at it, it kind of lends itself to the integral test only for this reason, that what you see down here, it's being squared, has a derivative that's a factor of the integrand's position. Now I gotta confess, you should show a few things. Do you mind if I save time today in class? You need to check to see if this is always positive, or forget it, I misspoke. From 1 on up, it is. You should check to see if it's decreasing. If in doubt, what do you do to check it? First derivative, build a sine graph and see if you've got your monotonic and strictly decreasing from 1 on out. And then thirdly, make sure it's continuous. But shoot, I think this thing is undefined when n is equal to 0. But shoot, I'm starting at n equals +1, no big deal. Oh, I misspoke, or I missed something. This is going to be undefined when n is equal to 0 as well. Again, it's just outside my interval, I don't care. And sometimes you're going to have to check that. It's not going to be that straightforward. So if you don't mind to save some time on the clock, I'll just dive in. I will look at the corresponding improper integral from 1 on up of my, you guys just tell me if I'm writing this down incorrectly.
No.
Oh, thank you. I didn't mean that.
So, okay, I have a question.
Yes. They'll just
What if
keep
it,
that.
so if it is discontinuous at, like, let's say 3 or something, you can't split the integral up like you did there and take the limit?
Do you see why? I mean, technically speaking, if I had something like this, I mean, if you look at the corresponding function, since I'm not continuous at x equals 3, then why bother taking a look at an integral like this? I know there's a limit out front. Because technically speaking, the fundamental theorem doesn't apply. The fundamental theorem of calculus. Now, I know maybe you can get around that. You can say, well, jeepers, just go ahead and split this up into 2 other integrals, treat them as improper integrals, because I've got an infinite integrand, and go from there. But I have to confess, you know, this is going to correspond to this series, and I think when n is equal to 3, I get infinity anyways. I wouldn't even go there if that were the case. Because I think an a sub 3 is going to be infinity. I know I clearly diverge. I just think it's silly to be continuous. And besides that, when you look at my proof, the proof doesn't even work if I'm not. If I got those gaps. So you guys, let's check it out. What substitution do you want me to make?
Don't you want to check and see if it's increasing or decreasing first?
Yeah, can I skip that?
Oh, yeah, then make a u sub for ln of x.
So first do one. First do one.
Oh, change it so it's a limit.
Thank you. So I got the limit as t plays this typical game from 1 to t. Oh shoot, now I got a proper integral. I can deal with this. So am I looking at partial fraction decomposition or integration by parts?
Neither u sub.
Neither, just a quick u sub.
When you give it to us on the test, are you gonna ask of us to use the integral test, or do we have no?
Absolutely not, nowhere in sight. Every question will be, does this converge or diverge? And you have to decide what test you're going to use. By the way, I'm starting off with the worst. I think this one involves too much work. I think the other ones are easy, personally. And if we commit to a u sub, are we experts at this?
Yes.
We are. Good, thank you. You said experts.
Well, not that
natural
good.
log of 1. No,
Which
zero.
is?
0.
Thank you.
And natural log of t.
Thank you. Yes or no? Absolute piece of cake?
Yes.
Good. I'm glad you agree.
10
Inverse tangent.
You tell me if I'm skipping too many steps. But you didn't bark at me when I said you're experts in integration.
That was rhetorical. What's going on?
I can't see past your head. All right.
So,
Thank you. I agree. Do you guys agree?
5 times natural t.
How is,
Wait.
0.
All the way. Linda?
Oh, I see it. Okay.
Oh, okay. Yeah.
It's approaching 5 halves.
It's probably, yeah.
That's your L.
What's my conclusion?
It converges.
Via the
Bagel.
integral test. Thank you. Therefore, if I can, it's clumsy in my room. Therefore, my series converges by the integral test. Well, you guys, speaking of the integral test, let's go back, talk about a function that's continuous, decreasing, and positive. Here's my M9. And with my blue pen, let me go ahead and put in this business. This is the same as A sub. Everybody there so far? What do you think you could say about just everything beyond this particular value of x that I called n, relative to whatever remainder you get, and using the first n terms to approximate a series? All right, I'll rephrase that. What can you say about the relationship between these two? Sum as I ranges from n on up of the a sub i's relative to the integral from n on up. Which one's bigger? Yeah, I think in the picture, clearly the corresponding series is going to be bigger, isn't it? Because the area of those rectangles in blue is bigger than the area underneath the curve from in on out. Are you guys with me?
Yes.
What do you think you could say about the relationship between these two? I'll change colors. And maybe it'll steal my same picture. By the way, in red what you see is a sub n plus 1. I think what you see in red here is a sub n plus 2. Here you see an a sub n plus 3. Let's talk about a relationship between two things. Number one, sum as I ranges from n plus 1 up to here, of the a sub i's. How does that relate to the area underneath the curve?
Small.
Ah, I can't write it. So this is going to be smaller. Do you guys agree? And so I think I've got bounds above and bounds below for the corresponding sums in my picture. That being the case, maybe you and I can dive in, and next time in class I want to talk about series, find some way of bounding above and below some upper and lower bounds for the evaluation of these particular sums. We'll talk about them.
Just do some sort of a Simpsons formula to get an exact
You know, I don't think you have to get that far
Okay.
at all. I think I get some bounds that are pretty darn close, then we'll run with it.
Okay.
Whatever, what I'm going to do next is talk about some few tests. Specifically, I want to talk about something called the comparison test. And the comparison test says the following. Here's my particular series. I want to be able to compare it to another series, and if my series has an nth term that's less than or equal to the nth term of another series I know converges, then my series is going to converge. In addition, if the nth term of my series is at least as big as the nth term of another series I'm comparing to, and I know that that other series diverges, then my series is going to diverge as well. Specifically, here's what's going on. Here's my series. Well, at least this is the nth term of a sequence of partial sums of my series. And here's the other one I'm comparing to. Well, you guys, maybe not, but at least the nth term of the sequence of partial sums for the series I'm comparing to. And if you take a peek at the infinite series I'm comparing to, let's suppose it converges. Let's check out what happens. Keep in mind that with my particular series and the other one, they've only got positive terms. And since there's only positive terms, what the heck do you think you can say about this particular sequence? Anything?
It's always positive.
You're right, each term is positive, but what else can you say about the sequence of partial sums here?
Increasing monotonic.
I think it's increasing. I think it's monotonic because each time I add another a sub n plus 1 or whatever it is, the subscript, I'm getting larger. Maybe not significantly larger, but I'm getting larger. It's monotonic. But if I'm assuming that this particular infinite series I'm comparing to is also convergent, then it equals a finite value. And since my s sub n is less than or equal to my t sub n, which is strictly less than my t, I think I'm bounded above and monotonic. Therefore, by the monotonic bounded theorem, I know that my particular sequence converges. But if the sequence of partial sum converges, then my particular infinite series converges. By definition of convergence for an infinite series. So I think trivially, this particular theorem is true. The comparison test is a theorem. On the other hand, if this particular series diverges, can I not talk about that? Because if it diverges, that means its nth term does not go to 0. But I think since my term is bigger than its term, and since this one doesn't go to 0, then mine's not going to go to 0 as well. Therefore, my series clearly diverges. I think that's trivial. So, that's my comparison test. Now, before I dive into some examples, if you guys don't mind, if I'm not saying too much, sometimes when I'm trying to compare my series to another, I'm pounding my fist on the table because I come so close to missing the question, but I just don't get quite the right relationship. There is an alternative version of this comparison test. I call it the limit comparison test. You check out what the limit comparison test says. Says, if I've got my series, I'm trying to determine convergence or divergence, and I compare it to another series I know converges or diverges, then here's what's going to happen. If the limit of my nth term to the other series I'm comparing to is nth term, as a ratio, if that limit is equal to a constant which is strictly positive and finite, then my series does what the other series does. It converges or diverges. However, if I'm comparing to another series that I know converges, and this ratio ends up being equal to 0, then I know my series converges as well. In addition, if I take the limit of my nth term to the nth term series I'm comparing to, but the nth term series I'm comparing to diverges, and this limit ends up being unbounded, that necessarily means my series diverges as well. So I have to confess, this is pretty strict. L's got to be non-zero. It's got to be finite, not infinity. But technically speaking, I've got a couple subcases that are easy to verify. And I think to verify this particular theorem, this test, its validity is an absolute piece of cake. Watch. Let's take my a sub n over its b sub n. And let's suppose this limit is a finite fixed real number. Then for values of n large enough, I'm certainly going to be sandwiched between two numbers. How about big M and little m? And now if I get rid of fractions and double inequality, then jeepers, at this stage of the game, I'm going to have the same argument I just erased. Applying the comparison test, my conclusion is immediate. So that's my derivation or verification of the limit comparison test. You know what, you guys? I made a mistake in terms of organization. I really did. I just verified and gave you both the limit comparison test so I could dive into some applications of it. I can't. I'm kind of limited. Can I take a small, 3-minute break? Because typically what you're going to compare your series to, typically, not always, typically, is a geometric series or something I call a piece series. And I haven't mentioned a piece series. So here's my 3-minute break. It's a series of the following form. 1 over n to the p power as n ranges from 1 on up. So let's see for what values of p this particular p series converges, and for what values of p does diverge. I'm going to cheat. I'm going to hand wave, because I snuck in the answer a few weeks ago. Yes, please, go back.
What if you messed up and put B over A?
You know, I gotta confess, for the first part of the theorem, it's not gonna be significant at all. Because if this ratio gives you a finite fixed real number that's non-zero, but non-infinite either, then its reciprocal is gonna do the same thing. It's just that it's gonna flub up down here, especially these things. And I gotta confess, you guys, that the upside to the math text we're using in the summer, I at least discuss these options. A lot of the math texts out there for calculus don't even mention this. They only give you this weaker version of the limit comparison test. Linda, did I answer your question? So everybody, come over here. I'm going to hand wave. I'm going to use the integral test. You take a peek at what happens with this improper integral. Have you seen this before? Yeah, you have. You have a test this next Tuesday, right? So this improper integral converges when
P is greater than.
p is greater than 1. And when p is not greater than 1, this improper integral
Diverges.
By the way, if p is bigger than 1, what's the evaluation? I asked, what's the evaluation symbol?
Bigger than 1?
Wouldn't it be if,
Whatever p value.
Thank you. Do you guys agree? We proved that in class.
yes,
That being the case, consider the p series. Clearly, by the integral test. It converges. For values of p strictly bigger than 1, and diverges otherwise. You guys don't take this the wrong way. Check out this particular list I've got on the board. I've got other tests. I just go back to my examples. Steal a few, get some practice with this particular new test, or both these new tests. Comparison test and the limit comparison test. Oh, here I don't know, you guys. You take a peek at my first example. Do you recognize the notation factorials? We talked about it in the past, right?
Yes.
Okay, I hope so. Any ideas?
converges,
Why?
because it's growing bigger
Then what?
than n. It's, yeah, so if n increases, it's going to be n factorial at the bottom, which would be like, say if n was 5, it's going to be 5 times 4 times 3 times 2, which is just going to grow incrementally as it increases to infinity. So it's going to get closer to 0.
But just because the nth term of my series goes to 0 doesn't mean my series converges. Let me give you an example.
Well, if n was on top, then it would diverge, right? If n was, or if n factorial
Well,
was in
clearly
the
you've got to
numerator.
test for divergence and diversion in that case,
Yeah.
yes. You guys check out this particular series. Yes or no? Does it converge or diverge? That was a bad question, wasn't it?
It converges.
Yes or no, does it converge?
Yes.
What do you mean no? Why not? Because it's a p series. P is equal to 1.
Okay.
And since p is not strictly greater than 1, I think the series diverges. By the way, this is such an important series, I give it a name. Maybe you know what it's called? A harmonic. It's so important, you guys, for the next couple of weeks, I'll use that name for it. And I maintain the harmonic series clearly diverges, and I can verify just by taking a peek at the left board and say, yeah, it's a p series with p being equal to 1. So it diverges by the p series test. However, I don't like the ends though, because I think, Bradley, here the nth term goes 0. It just doesn't go 0 enough for me to converge with the series. So, when you take a peek at my next example, number 10, I think if you're going to tell me whether converges or diverges, you have to use one of our tests. For example, the integral test says what? The integral test says
Nothing.
yeah, you're in such trouble. Because you and I don't have a corresponding continuous function that matches the factorial function. Well, not yet. There is one out there called the gamma function, but that's beyond our scope. And so I give up on the integral test. I think I should rely on the comparison test. I think you and I should take the nth term of our series, which, by the way, is just this, and compare it to something. Any ideas? 1 over n squared.
Because the n-factorial would be increasing much more rapidly than n squared. So it would always be less than 1 over n squared. Therefore it converges.
I suppose you've got a good point. It's just to do that, you're going to have to somehow tie it into the previous factors over here and talk about those previous factors being bigger than n itself. You'd have to do that. You could probably make it work. It's just a bit of work. What about this? Is that true?
Yes. No, it's not equal to.
Oh shoot, you're right. It didn't work. What about this?
No.
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 Why not?
Well, because on the left side that's 6, and then on the right side that's 8, and 8 is not equal to 6.
Oh, you're right. It's still not working, isn't it?
Yeah.
Let's do it again. What about 1 times 2 times 3 times something bigger like a 4? Do you think this is going to work? Oops, excuse me, hold it. I made a mistake. I don't know. Is that true?
Yes. Yeah.
Yeah, I think it is. Because technically speaking, this product over here is bigger than that product. So this fraction's smaller than this one since their numerators are the same. What would happen if I did this with a 2 add another factor, the next one up, but add another factor 2? Well, now this denominator is getting even bigger than over here. And now with my red pen, if I added a factor of 6 over here, but another factor of only 2 over here, here too this denominator is getting even larger. With the same numerators, that means this fraction is getting smaller. And so I think with my argument over here, I think this fraction right here is indeed less than or equal to 1 over 2 to the nth power, as long as n is at least as big as, I forgot, I didn't check. 4, thank you.
Why are you using 2?
So,
'Cause
I don't get it.
Because this is a geometric series, with r being less than 1 in absolute values. So Bradley, you don't get it.
Yeah, because 2 times 3 times 4, that is 24, right? Which is bigger than on the right side, which is 16.
And therefore this fraction's smaller.
Yes, but how is it equal to also?
Oh, it isn't. It's just that if this is less than that, that's still a true statement.
Okay, okay.
I'm just saying this is less than or equal to what's
Oh, okay.
I just wasn't being very careful. But it doesn't matter, does it? Well, check out what I just did, you guys. I took a peek at my nth term and found that it was bounded above by the nth term of another series that converges. Therefore, by the comparison test, my series converges. That's not good enough. Here's what I want you to write. Since 1 over n factorial is less than or equal to 1/2 raised to the power, which is the nth term of a geometric series. That converges. With my r value and absolute values being strictly less than 1, then by the comparison test, my series converges as well.
I have a problem with the 2. Because if you're giving me free reign to pick whatever number I want, you're going to get something ridiculous.
Really, why?
I don't know. I won't.
I just think
2.
when it comes to 3, it's going to take you a little bit longer. I was just trying to choose a convenient number down below for which I do see that this is a geometric series that converges, and I don't have to go that far out to figure out this relationship holds. But you know what? You're right. If you chose a 3 or 4 or 5 or 7 or 128, I still think we'll make the same conclusion. You just have to go out a little bit farther.
And so, why did you actually choose 1 over 2 to the n?
Because I could. I thought it was easy.
There's,
Because I was comparing, well, look, the product of 1, 2, 3, 4, 5, 6, 7, 8, eventually it's going to be bigger than 2 times 2 times 2 times 2, same number of factors of 2. I just thought 2 is a nice small number, so I didn't have to go down that far to get that relationship, nothing more. What about my next example? What do you think? Yes, sir.
So you don't have to say anything about it being greater than 4 in your answer?
No, I did with my work. I said this is less than or equal to that as long as, as long as n is greater than or equal to 4. I did say that in my work. What do you think about number 11? With what I've said, hold it, can I make this bigger, you guys? With what I've said so far, what can you say about the series and example number 1? Oh, really? Really? Why?
Because compared to 1 over 2 to the n again.
That was perfectly put. Check out my a sub n, the nth term, my series. Is it 2 to the n plus root n? Notice clearly this is less than or equal to 1 over 2 to the n, which I should say is just 1/2 to the n, which yet again is the nth term of a geometric series, where r is equal to 1/2, and therefore r in absolute value is less than 1. I think clearly by the comparison test, my series converges. Do you guys mind if I don't write that? Because this is exactly what I have written right here.
So the root n is irrelevant because it's smaller than 2 over n, or 2 raised to the n.
Can I change your words?
Yeah.
I would say the root n was irrelevant in that. Adding it, which is a positive number, to my previous denominator just made my denominator larger, which means this fraction can be smaller than n. I think that's why it works.
So if you wouldn't have done that, why couldn't you have used 1 over root over n if you proved that?
Why couldn't I use 1 over root n?
Yeah.
Well, good point, good point. So is this true, yes or no? Yeah, I think it's true. Therefore, same conclusion, right? My series converges by the comparison test. Everybody? No. The answer is no. I can't make that conclusion. Because look what I'm doing. I'm comparing the nth term of my series to the nth term of another series. And my nth term is less than that one, but by the p series this diverges. The comparison test doesn't apply. The comparison test says this. If my nth term is less than the nth term of another series that converges, I converge. If my nth term is bigger than the nth term of another series that diverges, I diverge. If my nth term is greater than the nth term of another series that converges, the comparison test is inconclusive. And if my nth term, like in this case, is less than the nth term of another series that I know diverges, the comparison test is still inconclusive. Did you catch that?
No.
Really? Okay, no, just too important. It's the subtlety of the comparison test. Can I say this again?
Yes.
Look at my nth term.
Yes.
My nth term is less than the nth term of another series I know converges. Well, I converge as well. Yes. The comparison test says this. If my nth term is less than or equal to the nth term of another series that converges, then my series converges as well. You guys imagine this scenario. Imagine this. What if my nth term is greater than the nth term of another series that converges? Then I think whatever happens, my series could converge or diverge. That's why you don't see it as written as a statement in the comparison test. The comparison test does not apply if my nth term is bigger than the nth term of another series that's known to converge. The comparison test is inconclusive. Let me say some more. What if my nth term is bigger than the nth term of another series that is known to diverge? Then I think clearly my sum's bigger than the other sum that already diverges. I think therefore by the comparison test, my series diverges as well. So one last case scenario. What if the nth term of my series is less than or equal to the nth term of another series that diverges? What do you think you could say about my nth term? It's inconclusive. Maybe I go to infinity, maybe I don't. Maybe I converge as a series, maybe I don't. Are you there?
Yeah. So just this other series?
Yes.
That's just something that we just or we just think up ourselves,
We
right?
think of ourselves, but I have
We
to
don't
confess,
actually
it
have-
better be a series you know converges to diverges.
So,
So it's typically it's gonna be a P series or a geometric series.
so like on a test or something, we wouldn't be given the series to
okay.
compare it to, we just have
No,
to
no.
come up with that? Okay. That's why
You
you
wouldn't want that, that would be.
did 1/2 to the end, because that's an easy one?
Yeah.
Is that always a good one to stick with, or?
Oh, no. That's what your intern looks like.
All right.
And besides that, Bradley, it's not the only test I'm gonna have.
Yeah.
But you guys appreciate, here's a beautiful thing that David said. Well, why can't I compare this? I can't. This is a true statement. It's just that's the end term of a series that I know diverges as a P series with PP equal to 1/2, which is less than 1. And since it diverges, my end term being less than its end term makes the comparison test inconclusive. Is that better?
So is there a particular order that we should approach these tests? Should we do the integral test first, or should we do the comparison
Good
test
point.
first?
When I'm done with all my tests that I'm gonna give you guys,
Yeah.
which is tomorrow, I will proclaim the integral test by far as the last thing you wanna look at. It's
Okay.
too much work, you gotta check the 3 prerequisites.
Okay.
So I wouldn't. So everybody, what about my next, can I restate all this? Can I change example number 11? Can I make it an 11.5? If I had this particular series, oh shoot, you guys, hold on, I made a mistake. This is another example, it's the same darn thing. I guess I have to do it because the comparison test still works. What's that? Yeah, I think I'm wrong. You look what I've written on the board. Actually, I think this denominator is smaller than that denominator, but the numerator is the same. So technically speaking, I think the direction of the inequality is different. I think the direction of the inequality is this way. Now what does the comparison test say? Now what does the comparison test say?
It's inclusive.
I think it's inconclusive. I don't think it says anything. Because I think now I've got my nth term, bigger than the nth term of another series I know converges, and the comparison test doesn't apply. But I came so close, and so I pounded my fist on the table saying, darn it, the comparison test almost worked. And often when it's the case when the comparison test almost worked, then just rely on the limit comparison test. Let's rely on it. Since the comparison test is inconclusive, the limit comparison test says this. Take a peek at the limit. Is n increased that bound of the ratio of my a sub n to b sub n. And see what happens. I think we get this. Or we get this. But I think if you were to take this out and use L'Hopital's rule, clearly that's going to go to 0. That being the case, it's limited value stuff. It's limited value stuff.
1.
1, and therefore by the limit comparison test, I think since this series I was comparing to, what the limit comparison test converges as a geometric series, then my series converges as well. No tricks. Ah, shoot. I snuck in 11.5, but to be honest with you, I guess 12 illustrates what popped in my head to talk about. Because here in 12, I think the same thing happens. This is a true statement, therefore the comparison test is inconclusive. Therefore I can limit comparison to 1 over 2 to the n. Do you guys agree?
Sure. So I have a question.
Yes, please.
So where do words come into play with these?
You were like in your final answer.
Yeah, well, like, should we say, like,
I think
census is almost true, or are we gonna use a limit?
No,
Do we
you
just
don't have to
label our
address this
test?
issue at this point. Now that you found the comparison doesn't apply, we jump to the limit comparison test, and here's what I demand to see. Something like this. We can change our words. But I demand to see you say something like after this conclusion. So, since this particular series I'm comparing to converges as a geometric series. With my R value being equal to 1/2, which is less than 1, and it's positive, then since the limit of the ratio of my nth term to its nth term, as that increases that bound, is equal to 1, which is strictly positive, by the limit comparison test, my series converges as well. I'm being a little sloppy, but it's something to that effect. Show me that you used the limit comparison test. Show me what that limit was. Show me it's strictly positive, that you understand what the test says.
Do you want it in MLA format as well?
No, not necessarily. No. I'm sorry for being sloppy. By the way, when it comes to the next test, sorry, you're not going to get that list of those tests. I want you to know, just like that. Oh, they're still up there. What about number 13, the unlucky question?
The next test, you mean the final?
Which is the final, yes.
So I mean, on the final, we've obviously got a lot of new material that's going to be on the final. How much old material is going to be on there, or is it pretty much all?
I don't know,
gonna be
that's a
new?
good question. I'm saying roughly 50-50.
Roughly 50/50.
That weekend before we take the final,
Yeah.
I will write the final, and so on the subsequent Monday, I'll be more clear. I'll give you a better idea what percentage, but right now I'm thinking roughly 50-50.
Okay.
Well, a lot of the new material will not encompass the old material, like the techniques and, or is the new material so different that you can't incorporate the old material within the new material?
I think the new material at the very end, the last week, will kind of be nice in the sense it does go back a little bit to what we did before. Not a lot, but a little bit. But I do think what I'm going to give you as material, as topics the last week, is light compared to everything else in summer.
Okay.
I think I'm saving the easiest for last.
And the length is gonna be the same. It's about the same.
You know, unless you and I can make an agreement on how much time we have for the final. You know, last exam we took, there was no agreement in this room whatsoever. Some people had classes afterwards, some people had to run the work. But if you guys are willing to clear your schedules, I'd be happy to give you more time.
Yes.
If it's going to
Please.
relieve the anxiety.
Yes.
If the people that have to go to work agree for the others, that it's fair for others to stay late, would that be okay as well? or-
We
No, it wouldn't, because that there would be a backlash. I can get in a lot of trouble for that.
Okay.
If you guys want extended time, we can talk about it, maybe not today, but start thinking about it, and if we can come to some universal agreement, I'm happy with that.
Or can we just do a two-part final, the first day will be the exam material, and the second day will be the final?
I know, but I feel like I'm rushing, just so I can save Wednesday to be a free day, so I don't come up with any material. I'm trying to finish the course on Tuesday. I just don't know if I can swing finishing on Monday. That's pretty tight. If something changes between then and now, I'll do that. I'll do that.
So when you say the end of the class, we're doing the easiest stuff, are you talking about chapter 10 or chapter 9?
I don't know. Is it 10? Yeah, whatever, let